Welcome back to Tech Talk Today, where we dive into the exciting world of technology, data management, and the complex systems that keep our digital lives running smoothly. Today, we're exploring a captivating topic within distributed databases, leaderless replication. It might sound a bit complex at first, but don't worry. We'll break it down into bite-sized pieces. We'll look at how leaderless replication operates, its advantages, and some challenges it brings along. So, grab your headphones and let's jump right in. To start, let's clarify what leaderless replication actually means. In traditional database systems, there's typically a leader node that manages write operations, while other nodes follow its lead. This can create bottlenecks and single points of failure. On the flip side, leaderless replication allows multiple nodes to accept writes at the same time, which can significantly boost availability and resilience. Picture this. You're a user trying to write data to a database. In a leaderless setup, your write request goes out to all available replicas simultaneously. Let's say you have 3 replicas. If 2 of them acknowledge the write while 1 is down, the operation is still successful, as long as you receive responses from the required number of nodes. This is known as a quorum write. In our example, if 2 out of 3 replicas confirm the write, you're all set. But this scenario raises an important question. What happens when one of those replicas is down? When it comes back online, how does it catch up with the writes it missed? This is where read repair comes into play. Instead of querying just one replica, the system sends requests to multiple nodes in parallel. This means you might get different responses from different nodes. If one node returns an outdated value, the system can update it with the latest information from another node. This process helps maintain data consistency across all replicas. However, it's not without its challenges. One significant issue with leaderless replication is the potential for stale reads. If a node has been down for a while and hasn't received updates, it might return outdated information when queried. To address this, version numbers are often used to track data freshness. When a client reads from the database, it checks these version numbers to ensure it's getting the most recent data. Let's also touch on quorum conditions, which are vital for maintaining data consistency. In a leaderless system, we define 3 key parameters, N, W, and R. Here's what they represent. N is the total number of replicas. W is the number of replicas that must acknowledge a write for it to be deemed successful. And R is the number of replicas that must be queried for a read operation to be considered valid. The crucial rule here is that the sum of W and R must be greater than N. Essentially, W plus R must exceed N. This ensures there's always some overlap between the nodes managing writes and those handling reads. For example, if you have 3 replicas and set W and R to 2, you can tolerate one node being down. That overlap is what helps maintain data integrity, even when nodes fail. Now, what happens if you decide to set W and R to smaller numbers? While this may allow for faster reads and writes, it also increases the risk of reading stale data. If the quorum condition isn't met, you might end up with outdated information, which can be a significant issue depending on your application's requirements. Another interesting aspect of leaderless replication is anti-entropy. This process helps synchronize replicas by copying missing data from one node to another. However, not all systems implement this feature, which can lead to inconsistencies if certain values aren't accessed frequently. If a value isn't read often, it might not be replicated across all nodes, reducing durability. As we think about potential pitfalls, it's worth noting that even with quorum conditions in place, stale values can sometimes slip through. For instance, if 2 writes happen simultaneously, it can be unclear which one takes precedence. This is where conflict resolution strategies come into play, such as merging concurrent writes or using timestamps to determine which write is the most recent. Moreover, if a write operation succeeds on some replicas but fails on others, and the overall write count falls below the required threshold, you may find yourself in a situation where the write is reported as failed, yet some nodes still hold the new value. This inconsistency can lead to confusion and stale reads. As we wrap up our discussion, it's vital to highlight the operational side of leaderless replication. Monitoring is key. Even if your application can handle some level of staleness, keeping an eye on your database's health is crucial. If replication lags significantly, it can result in outdated data being served to users. Implementing metrics to track replication lag can be incredibly useful. By measuring the difference between the leader's position in the replication log and that of the followers, you can gauge how well your system is performing. In conclusion, leaderless replication presents a flexible and resilient method for managing distributed databases. By allowing multiple nodes to handle writes simultaneously, it enhances availability and fault tolerance. However, it does come with challenges, particularly regarding data consistency and the risk of stale reads. Understanding the nuances of quorum conditions, read repairs, and effective monitoring practices is essential for leveraging leaderless replication in your applications. Thanks for tuning in to this episode of Tech Talk Today. We hope you found our exploration of leaderless replication insightful. If you have any questions or thoughts to share, feel free to reach out. Until next time, keep innovating and exploring the fascinating world of technology.